Welcome to the LibreOffice tips and tricks. Today I would like to do a simulation of a free cross-flow system. To imagine how it looks like, I made a small figure about it to explain. From top, the incoming water stream, for example tap water, will arrive into this buffer tank, a kitchen tool like a dish, and at the bottom we will make holes and the water can go out freely. And free cross-flow system simulation. We would like to simulate how the water level is changing and where will be the equilibrium, the steady state water level. I will insert the formula, the equations to understand how our calculation will happen. There is equilibrium between two energy. The kinetic energy and the potential energy will be equal. We have potential energy at the surface of the water. It will be somewhere as the water level increase, of course, higher energy, and the kinetic energy at the bottom. V on the square, velocity on the square. So you can see the equation here: mass times gravity acceleration times height. This will be the potential energy, and half times mass times velocity on the square. And this will be the kinetic energy. From this, the velocity is the most important for us. So it will be calculated as a square root of 2 times gravity acceleration times height if we solve this equation to express the velocity of the output stream. This will be here the velocity of the stream we calculated. From this, we would like to get the water level change. So how the water level is changing over time. Of course, it will be a difference of input and output stream, what drives this system. So the input stream minus output stream divided by the base area. The base area will be here at the bottom of the buffer tank, and combining the two equations, this previous part and the velocity including, we will see output in the index that the input stream minus the output cross section times the velocity will be the output stream over the base area. Okay, so now we have the equation, which will be the differential equation describing the water level change, and we would like to calculate only the water level from this. So I will modify this equation a little bit, that way that the time step will be on the other side, and the input water flow minus the output cross section times the square root of the 2 times gravity acceleration times height. I combined all previous equations all together, and everything is over the base area. So now we have the final equation. I have to enter into one cell to read more clearly these equations. I make the background more clear. Okay, so now we saw the equation as all of them we used, and finally this is what we have to enter. We need some constants. For example, what is the input stream, the output cross section, how many holes we have here, what is the base area of this buffer tank. I will imagine as a kitchen dish we use here. So the input stream will be in cubic meter per hour. Typically, if we use our tap water at home, it can reach 800 liter per hour stream. So I will transfer it to cubic meter per hour. It is 0.8, as 1000 liter is 1 cubic meter. But I would like to do my simulation in minutes, and in minutes I have to change this value. If I have 0.8 cubic meter per hour, only 60 parts will be in 1 minute, since 60 minutes will make 1 hour. I will already give a name to it. This will be the constant, and I will recall it with Q input in the equations when I have to input the formula. And after that, I have to know the base area. I will use a kitchen tool. Of course, it will be in square meter. And my kitchen dish would have 28 centimeter diameter. So how I have to calculate the area? The diameter on the squared multiplied by pi divided by 4. So 0.25 multiplied by pi and multiplied by the 0.28 on the square. So this will be the area in square meter of my kitchen tool. What will be the output area? I will make holes, 1 times 1 centimeter diameter hole. I will use my drill to destroy the kitchen dish and make the hole. Initially, I will calculate with only 1 hole, and maybe later we can increase the number of the holes. So the output cross-section where this output stream is leaving will be 0.25 times pi, similar to previously, and the 1 centimeter will be 0.01 on the square. Okay, so now we have these two area again, and the base I will calculate, name as a base, and the output will be a output. To be able to do the calculation, I still need the time step. Let's say we will calculate everything for 20 minutes. I hope it will be enough. In this case, it is suggested to have 0.2 minutes. With this, we will have 100 time points. It should be enough for a nice curve. So time in minutes, water level in meter, and the water level change again in meter will be the 3 columns we have to calculate. First will be the initial time 0 and the initial water level of 0 as well. The time frame, the time step, I also name as dt. Why I do this? Because I hate when people use the dollar signs in the formula. It is less readable. I will say that the time I will calculate the previous plus the dt time step. You have seen that as I started to type the name, it automatically suggested me. And the 20 minutes will finish pretty far. Oh yes, here. So now I have the 20 minutes in time frame with 0.2 time step. If I change this 0.1, you can see it is changing as well. So first I have to calculate with this last equation what is the water level change. Exactly, word by word, I will do this. dt times, we have the constant of course, the input quantity minus the output section, cross section, times square root 2 times gravity acceleration times the current water level. Now we have with the top part of the formula, and then divide everything with the base area. and you can see why it is very nice to use names. As I start typing the name, it is automatically suggesting me. And when you check this formula, you can see that it is much more readable than with a lot of cell references and dollar signs. It is more easy to understand. Now, how comes the next time step? For time step 0.2, we can calculate the water level as the previous one plus the calculated change. So now I can copy down, and of course I will copy with double click these two. Now we can see how it will finish. So I will make a chart to see the result of our calculation. Scatter plot, of course, because we have the x and y data, time, and calculated water level. Now we can see that there is a problem. It is a pretty straight line, still increasing continuously, and it is already over 4 meters. I don't know what kind of kitchen tools you have at home, but my dishes are less than 4 meters, hey? So for sure we have to think about this. I will add the other grid lines too. I prefer to have all grid lines because it helps a lot to read the values and identify all of them on the chart. It makes it more readable. The scale I will change to finish at 20 minutes since I simulated only the 20 minutes time, and of course titles are still missing. The x-axis will represent the simulation time in minutes, while on the y-axis this buffer tank water level we have water level in meter. Okay, so now the chart is finished and ready. We can see, oh, I don't want to cover the equation, and now you can see the simulation result. Maybe I compress a little bit and then it will fit one screen. Yes, we can see. And well, what is the problem? You can see that only one hole maybe is not enough. All around this dish I should have more. Let's say I will make 60 holes. Oh, that's much better. It goes until up to 0.4 meter. So the number of the holes, of course, definitely affecting the result of the calculation and the result, the water level. Where is the steady state? Now, looking at this chart, I have good news that we can reach the steady state. So this system is stable. This free cross-flow system, and the steady state water level is somewhere around 0.4 meter. Okay, that's much better than the previous, but still can be a little bit high. How we can decrease this water level? For example, what do you think will happen if I change this 28 centimeter diameter to a bigger dish and I use the 32 centimeter diameter? These are the typical sizes I can buy in the kitchen tool store. So if I change to 32, you can see the chart is changing, but the steady state level doesn't change. Only the way how we reach is faster or slower. So if I change back, you can see that with smaller diameter, smaller surface area here, it is faster. Slower with bigger and faster with smaller area. So we can make it slower, faster, but the steady state level is still this. How we can change the water level? Actually, we have to modify how many holes we make. For example, if I just increase to 65 holes, not 60, 65 holes, we can see that already around 35 centimeter is the steady state level. So now you can see how to calculate the water level of this free cross-flow system, and in this simulation we can see that it is a stable system with a steady state level, and we could investigate how sensitive it is to the base area and the output area. And we have seen that the number of the holes we make at the bottom are primarily contribute to the water level, and we can change that way. With the base area, we can only change the speed, how fast or slow we can reach the steady state level. Thank you for your attention.